Hey everyone, this is the next pre-lab talk for precipitation reactions, and this is actually the beginning of the next, what I've been calling mini unit. And so some of this will start showing up in future weeks, and I'll try to make sure I connect back to all of these things. As we've mentioned before, a solution is a homogeneous mixture of two or more substances that has a uniform composition throughout. The solute is the substance present in smaller amounts, and sometimes you can have multiple solutes. So again, going back to the easy example I always use, you could have salt in water or sugar in water and salt and sugar in water. And in all of those cases, whatever's present in smaller amounts that is being dissolved is your solute. The solvent is whatever is doing the dissolving. It's present in a larger amount. So again, some very common examples in a soft drink such as Coke or Pepsi. Your solvent is water. The solutes are sugar, CO2, anything else present in the syrup. There's lots and lots of solutes there, but the big ones would be the sugar and the CO2, the carbon dioxide that actually makes it bubbly. Air, the air we're breathing, is actually a mixture of a bunch of different gases. The main component in the air we're breathing is actually nitrogen. It's not oxygen. So nitrogen would be the solvent for that mixture, and oxygen, argon, methane, and a whole bunch of other trace gases would be the solutes dissolved into it. You can have solutions of metals or of solids. It's a little more difficult. They tend to create alloys instead that are heterogeneous mixtures. But if you make a homogeneous mixture of solids, which you can do, one example is soft solder, where the solvent is lead and the solute is tin. So you can have solutions of any phase of matter. It just really depends on, is it truly dissolved and homogeneous? And getting into concentration a little bit, you can have different aqueous solutions of potassium permanganate. And aqueous just means dissolved in water, telling us it's a solution. So this darker KMNO4 solution on the left means it has a higher concentration, and the paler one on the right has a lower concentration. And some of that we'll actually get into in future experiments, but you can see some differences based off of how much solute is in there as well. The other thing to discuss are electrolytes. Electrolytes are substances that, when dissolved in water, dissociate and create ions that can conduct electricity. So getting into this idea of solutions, if you dissolve something in water to create a solution and that solute dissociates and splits into ions, that compound is an electrolyte. There are non-electrolytes that do not dissociate and do not therefore conduct electricity. There are two different cases for why this may happen. Either A, it doesn't dissolve in what your solvent is, most of the time water. So for example, if you put sand in water, the sand's not going to dissolve, it's just going to sit there. Or you could have something that does dissolve but does not dissociate. So for example, sugar does dissolve in water but does not traditionally conduct electricity because it doesn't dissociate into ions. So if you were to put a light bulb with some leads into your solution, if there are ions in that solution, they will connect the two metal leads and turn the light bulb on. So for a non-electrolyte, it doesn't dissociate, there are no ions, it will not conduct electricity. A weak electrolyte only partially dissociates. So there are some ions, which is why the light bulb comes on, but there aren't very many. Strong electrolytes, however, completely dissociate into ions and therefore form lots and lots of ions that conduct electricity very, very well and turn the light bulb on very, very brightly. So in order to conduct electricity in the solution, it must break into cations and anions. Cations are positively charged, anions are negatively charged. So a strong electrolyte means it has 100% dissociation. all of what you put in there completely dissociates. A common example is NaCl, or table salt. When you dissolve it, the sodium and the chlorine split apart from each other into the positive and negative ions, and all of those dissociate to conduct electricity very, very strongly. As an alternative, there are weak electrolytes that only partially dissociate. Now, most of the time, this partial dissociation is very, very low percentages. So we're not talking about the difference between a strong electrolyte and a weak electrolyte being 100% and 90%. This is something more along the lines of a strong electrolyte is near 100% and a weak electrolyte's maybe under 20%. So oftentimes, weak electrolytes will be denoted with this double-sided arrow or an equilibrium arrow. And so, for example, C3COOH, or acetic acid, which is the primary compound of vinegar, is a weak electrolyte. It does split into the H+ and acetate ions, but a lot of these will also recombine to form the acetic acid, which will then break apart, and you get this equilibrium back and forth. So at any given point, you don't have very many separated ions, which is what makes this a weak electrolyte. Most of the time, if we're looking at a double displacement reaction in chemistry, a lot of the reactions we will be dealing with are called double displacement reactions. And they all take the form of AB plus CD, where A and B are the positive and negative ions of the first compound, and C and D are the positive and negative ions of the second compound. So we can think about it as these different triangles. And what's going to happen is when you put them in water, they will dissociate. Most of the time, double displacement reactions are looking at strong electrolytes combining to form something new. So each of your compounds will break apart when put into water, and they won't recombine as, for example, A and B won't come back together because that's a strong electrolyte. It'll just immediately dissociate and break apart again. A and C can't come together because they're both positively charged, or in this case, the triangles don't fit together. So the only option is A combines with D and C combines with B. And so you create these new compounds, A, D, and CB. So overall, what a double displacement reaction looks like is you have one compound of two ions, a second compound of two ions, and they flip places to create two new ionic compounds. Now, what is important about those is the new things you make, one of them has to not be a strong electrolyte. If it immediately just breaks apart again, then you're not going to see anything. But if you form a solid or a gas or liquid water or something, now you see a new compound that stays around. As an example, silver nitrate and calcium chloride. We can bring these together and create some new compounds. So to figure out what we're going to make, we need to break these molecules into their cations and anions. And this is where you will need to know how to read a periodic table, and you're going to want to know your polyatomic ions. For this class, you don't need to memorize your polyatomic ions. There should be ways for you to figure it out or have it provided to you for each question. Again, if you ever run into issues where you think I haven't provided something that you needed, that you haven't been told you needed to memorize, please just let me know and I will fix that. So for silver nitrate and calcium chloride, our A and B for silver nitrate are going to be silver and nitrate. So silver is a +1 cation, nitrate, NO3 is a -1 anion. Calcium chloride is Ca2+ and Cl-. Now, silver is one that you would just have to memorize. Nitrate is a polyatomic ion you would just have to memorize. Again, there will either be ways to figure this out or it will be provided. But calcium chloride, there is a way to figure it out. So if we look at a periodic table really quick, we're looking at calcium chloride, CaCl2. We look at calcium, it's right here. This is in group 2. This means it has 2 valence electrons. All atoms, when they combine, are either trying to get to 0 or to 8. And the reason they try and get to 0 is the next shell down will have 8 in it. So it's something called the octet rule. But if you're looking at it in this way, if you're just looking at valence electrons, the atom, when it forms an ion, wants to get to 0 or to 8. So calcium has 2 valence electrons. It's either going to lose those 2 or have to gain 6. And it's always going to be easier to gain or lose the lower number. So calcium in this case will lose 2 electrons and become a +2 charge. If you lose 2 electrons, electrons are negative. You've lost 2 negatives, so you have extra positives. A little counterintuitive. Chlorine, on the other hand, has 7 valence electrons. It's in group 17. The most number of valence electrons you can have is 8, as far as this class is concerned. So 17 is not an option. You just look at the ones place. So if we're going to go across the periodic table, group 1 has 1 valence electron. Group 2 has 2 valence electrons. The transition metals, you can't look at their group numbers. They do all sorts of strange things. But when we get over here to group 13, these will have 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, and 7 valence electrons as we move across. The noble gases over here do have 8 valence electrons, which is why they tend to not form compounds. They're already full at 8. Some periodic tables you may see might have these main block that we were just looking at numbered as 1, 2, 3A, 4A, 5A, 6A, 7A, and 8A. If so, that number tells you how many valence electrons it has. But again, we're looking at chlorine, group 17. We care about the ones place, so it has 7 valence electrons. So it's either going to lose 7 or gain 1. In this case, it will gain 1 electron. Because it has gained a negative charge, it becomes a -1 ion. So if we go back to look at our compound, calcium makes a 2+ charge because it will lose those 2. Chlorine makes a -1. I'm not going to get into balancing chemical equations and where some of these things come from because that'll be in the next experiment. But once we split all of these into their ions, we can combine the new things together. Now it's apparent. We already had silver and nitrate together, so that's not anything new. We can't combine a positive and a positive. That'll never work. We can combine a positive and a negative to make AgCl, silver chloride. When we combine calcium and nitrate, this is a +2 charge. We'll blow this up. There we go. Calcium is a +2 charge, and nitrate is a -1 charge. These are not balanced when you bring them together. You would still be left with a +1 charge. So what you have to do to bring these together is you have to create a balance between these pieces. One of the shortcuts you may have heard is you can take their charges and make them subscripts. So for example, the calcium is going to give its 2 to nitrate, and the nitrate is going to give its 1 to calcium, which is why in the combined formula, nitrate has a 2. But make sure you can correctly form these compounds. That's going to be a big part of this experiment and the quiz and the post-labs. Other thing to note, whenever you're writing a polyatomic ion that also has a subscript, make sure you put the polyatomic ion in parentheses. Otherwise, this would look like CaNO32 or 32, and that's not the correct formula. So make sure you put those in parentheses around your polyatomic ion. The other thing to note, if we look down here, this 2 that was on the chlorine did not carry over to the other side. We don't have it over here. That 2 is there to balance charges. Again, if we were to go back and look at the original equation, calcium is a 2+, chlorine is a 1-, so we would have to swap those charges to make their subscripts, which is where this 2 came from. That means subscripts do not inherently carry over from one side of the reaction to the other. Only subscripts associated with polyatomic ions will. And hopefully through this class, you'll start to get accustomed to which ones are polyatomic ions and do carry over. Everything else, all of the other subscripts, will not carry over because they are based on charges. So if you ever have a question, make sure you can look up the polyatomic ion, either in the question or if you're working on a post lab online, and that will tell you what subscripts do carry over. Now, I do have a note that this equation isn't balanced. We don't care about balanced chemical equations this week. That'll be next week's issue. All we care about is what compounds did we form. So the reason being able to form these compounds is important is because of something called precipitation reactions. And I mentioned this way back in chemical and physical properties. A chemical property is if you mix two liquids and they form a precipitate. Well, now we're talking about it. So a precipitate is an insoluble solid that separates when you mix two liquids together. A really easy example is lead nitrate and sodium iodide come together to make lead iodide and sodium nitrate. If we look up solubility rules, what we'll find out is the lead iodide does not dissolve, it does not dissociate, it actually falls out as a solid. So if you were to mix these two liquids together, they're actually both clear liquids. You mix them together and you get this yellow solid that kind of drifts down. That yellow solid is your lead iodide precipitate. And this is what's called the molecular equation. From a molecular equation, you can create what's called a complete ionic equation. Anything that is aqueous, anything that's dissolved in water and is a strong electrolyte, which most ionic compounds will be separated into their respective ions. So lead nitrate breaks into lead with a +2 charge and nitrate with its -1 charge. Sodium iodide breaks up into sodium with its +1 charge and iodide with its -1 charge. Again, lead is a weird one. It's one of the transition metals. You would not be expected to know how to find its charge. That would be provided. Nitrate would either be provided or you would have some other way of identifying it. Sodium you should be able to figure out. It is a group 1 metal, so it will make a +1 charge. Iodide is a group 17 element, so it will make a -1 charge. We can do the same thing on the reactant side of the equation. The left side is our reactants, the right side is our products. This is what's produced. So we can do the same thing with our products. The solid does not break apart. We carry it down as is. The aqueous sodium nitrate, we will break apart into sodium as a +1 and nitrate as a -1. Then we can do something where we cancel out everything that's the same on both sides. So for example, both of those nitrates will cancel out. The sodiums will cancel out. They're the same on both sides, just like you do with algebra. If you have 3x and 1x on the other side, the x's will cancel out. You can do the same thing here. And everything that's left gets written down as your net ionic equation. So I'm not going to ask you guys to create net ionic equations, but you should be able to look at a molecular equation and a net ionic equation and figure out how to get from one to the next and what pieces are missing. The things that are crossed out are called spectator ions. So in this case, sodium and nitrate are spectator ions. So realistically, what's happening in this reaction is what's shown in the net ionic equation. The lead and the iodide are coming together to form lead iodide as a solid. Everything else is really just a carrier to get those ions to come together. And that's what we're looking at with precipitation reactions. So basically what we have happening, we flip to potassium iodide instead of sodium iodide, the same things happen, but all of these red and white molecules are water, and we have our potassium iodide that breaks apart in solution. We have our lead nitrate that breaks apart in solution, and all of these things bounce around until the lead and the iodide come together, and then they stick together and drop out of solution. And this keeps happening over and over and over until all of the lead and all of the iodide come together, react, and fall out of solution. If the potassium and the nitrate were to come together, that's fine. They would make potassium nitrate. Potassium nitrate is a strong electrolyte, so it immediately breaks apart again when it's dissolved in water. And so we get this lead iodide precipitate that forms at the bottom. And that's what our net ionic equation is showing us. From beginning to end, the only thing that changed is the lead and the iodide ions came together to form something new. Everything else basically stayed as it was. And that's the yellow solid we see when we mix these together. So as a solubility table, this will be provided to you for any quizzes or for the final exam or anything like that. If you need it during the post-lab questions, you can access it through the PowerPoints, you can Google it, there's all sorts of options to get a hold of it. But for anything that's a testing scenario like the quiz, we would provide this to you. You do not need to memorize these. So your soluble compounds, these are things that are generally soluble. For example, your alkali metal ions or your group 1 metals, lithium, sodium, potassium, rubidium, cesium. These things tend to be soluble. The insoluble exceptions are absolutely none. So if you have a compound with one of those ions in it, it will be soluble always. If you have the ammonium ion, NH4+, this is one of your polyatomic ions, it will be soluble with no exceptions. It will always be soluble. Same thing for nitrates, acetates, bicarbonates, chlorates, and perchlorates. All of these are additional polyatomic ions. So again, you wouldn't need to know the names and charges because they would be shown on this solubility table. That's what I mean by you might be able to go find it if you need it for a quiz. But these anions are also soluble with no exceptions. So if you have a compound composed of these, it will be soluble. And all it takes for a compound to be soluble is one of the ions to be soluble. So for example, sodium nitrate is definitely super soluble. Both pieces are. But if you were to have, for example, what we used earlier, silver nitrate, because the nitrate is soluble, the whole thing will be soluble. So now we get into some of the soluble ions that have exceptions. Your halides, chlorine, bromine, iodine. These are your group 17 halogens. If you have one of these in a compound, it is probably soluble. It will be soluble unless the other thing is attached to is silver, mercury, or lead. If it is attached to silver, mercury, or lead, it will become insoluble and precipitate out. So if we go all the way back to the example reaction I was using earlier. What we created from our silver nitrate and calcium chloride was silver chloride. So if we were looking at these, nitrate is soluble, so it's soluble. Halogens are soluble unless they're attached to silver, mercury, or lead. This is not silver, mercury, or lead, so this will be soluble. Nitrate, always soluble. Silver chloride. Chloride is soluble unless it's bound to silver. So AgCl would be our solid from this reaction. And that's how we can use solubility rules to identify our precipitates. And that's really what you're going to be doing this week. Sulfates, again, are usually soluble unless they're bound to silver, mercury, lead, silver, mercury, lead, calcium, strontium, barium. Then on the flip side, we have things that are generally insoluble. Carbonates, phosphates, chromates, sulfides, and hydroxides. The exceptions to these is if they are bound to a group 1 metal, they will be soluble because that goes back up to this rule. It's a group 1 metal, it's soluble with no insoluble exceptions. So these rules, the group 1 metal's solubility overrides the insolubility of these anions. The ammonium ion, again, is another one that if it's bound to that, it will be soluble. The only other exception for hydroxide specifically is if you have barium hydroxide, it will be soluble. So that's how you read this table. Make sure you're comfortable using it. You will need it for this experiment and for the quiz and moving forward. So again, here's some colorful examples of ionic compounds. We have cadmium sulfide, lead sulfide, nickel hydroxide, and aluminum hydroxide. So you can get these different colors depending on what compounds you have that are forming your precipitate. So again, walking through how to write the net ionic equation like we talked about earlier. A balanced molecular equation for now will be provided to you. Next week, when we talk about how to create a balanced molecular equation, you will need to create those after next week. But from that balanced molecular equation, you can split everything apart using the strong electrolytes that are completely dissociated into cations and anions. Cancel out the spectator ions that are on both sides, and then check to make sure at the end that all of your charges and number of atoms are balanced. And again, you can go back and look at the previous example, or if you have questions, reach out to me. You'll be doing a lot of this with the post-lab questions, so that'll really help you get through being able to predict these products and making ionic equations. The experiment itself is very, very easy. Like week one, we're mixing a whole bunch of stuff together. So what we're going to do is we're going to mix all of the different reagents together and write down what we see. And you'll see all of that in the experimental video. So we've got these 7 liquids that we're going to mix together. Anything that's the same, we don't need to worry about mixing, and anything that's a duplicate of a mixture, we won't need to worry about mixing. So for example, this first one, if we mix NaOH and NaOH, guess what? We're going to get NaOH. There's nothing new, there's no reaction that can happen there, so we don't need to worry about it. However, if we mix NaOH and NaNO3, we could have a reaction here. We could get something different. These aren't the same compound. And so we will mix it and you'll see what happens. Same thing for sodium hydroxide and iron chloride and all the way across. Now, if we were to look down at this second one, that's mixing sodium hydroxide and sodium nitrate, which is exactly what we did in this first mixture here. So there's no reason to duplicate it. So when you look at the pictures in the tables, you'll have things filled in for this kind of top half triangle because there's no reason to mix anything that's a duplicate of either itself or of a mixture we've already made. So again, that's it. Make sure you watch the experiment video. The post-lab questions are where you're really going to start nailing down how to predict these products and how to analyze precipitate reactions. And we'll use that next week in another experiment. So make sure you really cover this well and make sure you can do this. Thanks, guys.